The emptiest places in the known universe are not in fact empty at all. They are teeming with unseen travelers, ghosts on a journey of 1,000,000 or 1,000,000,000 years. These are the spaces between the stars, the colossal silent oceans of the cosmos, where the light of one sun fades into an imperceptible whisper before the light of the next can be heard. For millennia, we imagined this interstellar gulf as a sterile void, a near-perfect vacuum populated by nothing more than stray atoms of hydrogen and the faint echoes of the Big Bang. We saw the stars as islands of frantic, fiery activity, and our own solar system as a cozy, isolated harbor walled off from the greater galactic sea by the sheer tyranny of distance. We were wrong. This profound emptiness, it turns out, is a highway. And down this highway travel objects of incredible antiquity and mysterious origin, castaways from planetary systems we may never see, carrying with them the chemical secrets of their birth. They are time capsules from alien shores, moving at speeds so immense they defy the gravitational leash of any single star, including our own. For all of human history, these cosmic pilgrims passed us by in complete anonymity, silent ships in the eternal night. We had no telescopes powerful enough to spot their fleeting passage, no inkling that our solar system was not a closed sanctuary, but a temporary crossroads on an infinite celestial map. We were content to study our own family of planets, our local neighborhood, believing it held all the clues we needed to understand our place in the cosmos. But the universe had a surprise in store for us, a message in a bottle that would shatter our comfortable isolation and force us to confront the true, bewildering nature of the galaxy we call home. It began in 2017 with a phantom, a flicker of light moving so fast and on such a bizarre trajectory that it made no sense. Astronomers named it Oumuamua, a Hawaiian word for a messenger from afar arriving first. The name was an understatement. This object was not just from afar. It was from another star system entirely, the very first one we had ever confirmed. It was a thin, fleeting whisper from the void tumbling through our solar system on a path that would ensure it would never ever return. Our encounter was tragically brief. We saw it only as it was leaving a faint point of light, already racing away from the sun and back into the abyss. We threw every telescope we had at it, desperate to capture any detail, any clue about its nature. But Oumuamua guarded its secrets jealously. We couldn't get a clear image. All we had were its strange properties, a collection of riddles that grew more profound with every observation. Its light curve, the way its brightness fluctuated, suggested a bizarrely elongated shape, perhaps like a cosmic cigar or a flattened shard-like pancake, unlike any asteroid or comet we had ever seen. Even more mysteriously, as it sped away from the sun, it was accelerating. Something was gently pushing it, giving it an extra nudge that the sun's gravity alone could not explain. For a comet, this would be normal. As a comet nears a star, its ices vaporize, creating jets of gas that act like tiny rocket thrusters, a phenomenon called outgassing. But when we looked at Oumuamua with our most sensitive instruments, we saw no such thing. There was no dusty gaseous halo, no characteristic cometary tail. It was inert, silent, yet it was accelerating anyway. The scientific community was thrown into a state of exhilarating turmoil. What was this thing? Theories flew, each more exotic than the last. Was it a new kind of comet? One whose outgassing was composed of invisible molecules? Was it a pure hydrogen iceberg? An object theoretically possible but never before imagined, peeling away layers of frozen gas, in a way our telescopes couldn't detect. Some even dared to whisper a more radical possibility. The strange shape, the anomalous acceleration, the lack of a coma, all these were properties one might expect from a manufactured object, a piece of alien technology, perhaps a solar sail or a derelict probe tumbling through the interstellar dark for eons. We will likely never know for sure. Oumuamua is gone, having slipped back into the interstellar ocean, taking its answers with it. It was a frustrating, tantalizing glimpse of a universe far stranger than we had conceived. It proved that the messengers were out there, but it left us with more questions than answers. It was a cosmic ghost story, one that haunted the dreams of every astronomer. We had opened the door to the galaxy, and the first thing we saw was an enigma that defied all our categories. Then, just 2 years later, a second visitor arrived. This one was named 2I, Borisov, and at first it seemed to be the answer to our prayers, the key to resolving the Oumuamua paradox. As it swung into our solar system, Borisov behaved exactly as we expected an interstellar object to behave. It looked for all intents and purposes like a perfectly ordinary comet. As it warmed in the sun's glare, it grew a magnificent coma and a long, dusty tail. Spectrographs revealed the familiar chemical signatures of water, ice, and cyanide, the standard building blocks of comets from our own Oort cloud. It was a profound relief. The universe, it seemed, wasn't so strange after all. Borisov suggested that Oumuamua was the exception, the weird one-off, while the majority of these interstellar travelers were just like the comets we knew. It was a comforting thought, one that solidified our long-held theories. Our models predicted that the vast majority of objects ejected from forming solar systems would be icy bodies, planetary embryos flung out from the chaotic outer regions by the gravitational bullying of giant planets like Jupiter. These cosmic snowballs would then wander the galaxy for billions of years. Borisov was the perfect poster child for this theory. It was a piece of another solar system, yes, but it was a familiar piece. It told us that the chemistry and dynamics that formed our own solar system were likely common across the galaxy. We had seen the ghost, and now we had seen the machine. The mystery we thought was settling into a predictable pattern. We had established a baseline. We knew what to expect. We were ready for the next visitor. We believed we finally understood the rules of this great interstellar game, and that is when 3I, Atlas, arrived. And it didn't just break the rules, it vaporized the rulebook. Discovered in late 2022 by the Asteroid Terrestrial Impact Last Alert System, or ATLAS, in Hawaii, this third confirmed interstellar guest was initially just another faint speck on a collision course with our understanding. Its trajectory was unequivocally alien. The mathematics were undeniable. This object was not bound to our Sunday. It was a true creature of the interstellar deep, another priceless sample delivered to our doorstep. The astronomical world held its collective breath. What would this one be? Another baffling Oumuamua, or another reassuringly normal Borisov? For a while it seemed to be leaning toward the latter. As 3I, Atlas, made its long plunge toward the inner solar system, it began to brighten. It started to develop a faint coma, the hazy atmosphere of a waking comet. The familiar script seemed to be playing out once more. Scientists around the globe trained their instruments on the approaching object, ready to document another piece of supporting evidence for the galactic comet hypothesis. This time, however, we had an advantage we never had with Oumuamua. We saw it early. It was on a trajectory that would bring it much closer to our telescopes, offering an unprecedented opportunity for study. We would be able to dissect its light map, its chemistry, and watch its behavior with exquisite precision. But as it drew nearer to the sun, something spectacular and unexpected happened. The intense solar radiation and gravitational forces began to take their toll on the ancient traveler. The delicate fabric of this object, which had survived perhaps hundreds of millions of years in the frozen calm of interstellar space, began to fail. 3I, Atlas, started to fracture. It broke apart. For a mission controller, a disintegrating spacecraft is a disaster. For an astronomer studying a pristine object from another star, it is the ultimate gift. The breakup was a catastrophic event for the object, but for us, it was a moment of profound revelation. It meant we were no longer just looking at the dusty, weathered surface of this alien artifact. We were being given a direct, unobstructed view of its heart. The fragmentation peeled away the outer layers, exposing the core, the primordial material that had been locked away since its formation around a distant, unknown star. This was the moment of truth. Our theories, reinforced by Borisov, made a clear and unambiguous prediction about what we should see. Buried within the expanding cloud of dust and gas, we should find a nucleus made of dirty water ice mixed with rock, the classic composition of a cometary core. It would be dark, perhaps irregular in shape, but fundamentally it would be a familiar object, a cosmic snowball forged in the icy outskirts of another planetary system. The most powerful telescopes on and off the planet, from the Hubble Space Telescope in orbit to the giant Keck Observatory on Mauna Kea, zeroed in on the fading light of the fragments. The data poured in, computers churned through the complex analysis, filtering out the noise of the surrounding coma to isolate the light reflecting off the freshly exposed core material. The scientific community waited, anticipating the final confirmation, the photograph that would solidify our understanding of the galaxy's wandering population. And then the results came in, and there was a stunned collective silence. What the telescope saw looked nothing like a comet's core. Absolutely nothing. The fragments were not dark, icy bodies. They were intensely bright, far more reflective than any known comet in our solar system. The material was incredibly dense, and its spectral signature was bizarre, lacking the clear signs of water ice we had been so certain we would find. Instead, it hinted at a composition rich in refractory or heat-resistant materials. It seemed to be made not of ice, but of something closer to rock or even metal, forged in temperatures far hotter than the frigid zones where comets are born. It was as if we had expected to find a chunk of loosely packed snow, and instead found a polished ball bearing. Every model we had, every simulation we had run, was predicated on the idea that these interstellar vagabonds were icy exiles. 3I, Atlas, told us that this fundamental assumption, the very bedrock of our understanding, was profoundly incomplete, perhaps even flat-out wrong. This object was not a comet. It wasn't an asteroid as we would define one. It was something entirely new, a third class of object whose existence we hadn't even properly conceived of. Its core, now revealed to us by its own self-destruction, was not a relic from the cold outer edge of a solar system. It looked more like a piece of the innermost region, a fragment from the violent, fiery heart of a planetary system being born or dying. How could such an object forged in heat be ejected into the interstellar void? The physics required to do that are extreme, far beyond the gentle gravitational nudges that fling comets out of their orbits. It would require a cataclysm of unimaginable proportions, a planet being torn apart by its star, a supernova explosion, a gravitational collision of cosmic titans. The existence of 3I, Atlas's strange rocky core, doesn't just add a new specimen to our collection. It rewrites the entire story of what populates the space between the stars. It suggests that the interstellar medium is not just a cold repository for icy leftovers, but a graveyard carrying the shattered remnants of planetary destruction, a forensic record of the most violent events in the galaxy's history. The ghost of Oumuamua gave us a riddle. The arrival of Borisov gave us a comforting but false answer. Now the sacrifice of 3I, Atlas, has given us the truth, and that truth is a terrifying and exhilarating new mystery. We thought we were listening for whispers from the cold, but we've just found a scream from the fire, and we are only just beginning to understand what it means. Every visitor tells a story. For millennia, the only travelers we knew were our own, born from the same cloud of gas and dust that forged our world. They arrived in our skies as celestial phantoms, their ethereal tails stretching across the constellations like a brushstroke of divine warning. We called them comets. For most of human history, they were seen not as objects but as omens, unpredictable, terrifying portents of plague, war, and the fall of kings. They were celestial demons, their sudden appearance in the heavens, a rupture in the perfect clockwork of the stars, a chilling message from the gods. We looked up in fear, convinced these apparitions were harbingers of our own doom, their silent passage, a judgment on our world. It took the steady march of reason, the meticulous observations of astronomers like Edmund Halley, and the profound gravitational logic of Isaac Newton to finally tame these specters. They were not demons, but family. Distant, eccentric, but family nonetheless. They belong to us, bound by the same invisible leash of solar gravity that holds our Earth in its gentle, life-giving embrace. We learned to read their stories written in ice and dust. We came to understand them as dirty snowballs, magnificent in their simplicity, yet profound in their implications. These are not mere rocks, they are time capsules. They are pristine relics from the dawn of our solar system, born 4.5 billion years ago in the frigid, chaotic nursery where the planets were just beginning to coalesce. Cast out by the gravitational jostling of the giant planets, most were flung into two vast, dark reservoirs at the edge of our solar system. Some reside in the Kuiper Belt, a flattened disk of icy bodies orbiting beyond Neptune, a region populated by dwarf worlds and frozen planetesimals. But the true kingdom of the comets lies much farther out in the theoretical but necessary expanse known as the Oort cloud. It is a place of unimaginable scale, a ghostly spherical shell of trillions of frozen artifacts surrounding our entire solar system. This is the deep freeze, a celestial attic where the primordial building blocks of worlds have slumbered in an almost perfect vacuum, untouched by the warmth of our Sunday. From this gravitational hinterland, the slightest nudge from a passing star can dislodge one of these sleeping giants, sending it on a slow-motion fall toward the inner solar system, a journey that can last for millions of years. As one of these ancient travelers finally nears the sun, its story begins to unfurl. The gentle warming sunlight awakens the nucleus from its cryogenic slumber. What was once a dark, inert lump of frozen water, methane, carbon dioxide, and rock begins to sublimate. Ice turns directly into gas, erupting from the surface in violent jets and geysers. This process shrouds the solid core in a vast, glowing atmosphere of its own making. A transient bubble of gas and dust we call the coma, which can swell to become larger than the planet Jupiter itself. And from this glowing head, the true spectacle is born. The sun's influence splits into two distinct forces, each sculpting a unique and glorious tale. The solar wind, a relentless stream of charged particles flowing from the sun, grabs onto the ionized gas in the coma and pushes it straight back, creating a slender, bluish ribbon of plasma, the ion tail. This tail acts like a cosmic weather vane, always pointing directly away from the sun regardless of the comet's direction of travel. Simultaneously, the gentle but persistent pressure of sunlight itself pushes on the larger, heavier dust particles, creating a second, more diffuse tail. This dust tail is broader, brighter, and often gracefully curved, tracing the comet's orbital path like the wake of a ship. For a few brilliant weeks or months, the comet puts on the greatest show in the solar system, a temporary masterpiece of physics and light before it swings back around the sun and begins its long, lonely retreat into the cold and the dark. It's a sun. Story told. This was the universe we knew, a cozy, self-contained system. Our sun, our planets, and our comets all moving to a predictable gravitational rhythm. We had always assumed we were alone in this, that the vast chasms of interstellar space were just that, empty, an unbridgeable ocean between the islands of distant stars. Then, on a quiet night in October of 2017, everything we thought we knew was shattered by a single, faint streak of light. The Pan-STARRS telescope in Hawaii, designed to hunt for asteroids that might threaten Earth, flagged something impossible. It was an object moving at a staggering 196,000 miles per hour, a speed so high that the sun's gravity could not possibly hold on to it. When astronomers plotted its trajectory, they stared in disbelief. It was not an ellipse, the classic looping path of a comet or asteroid bound to our Sunday. It was a hyperbola, a perfect open-ended curve. This visitor was not turning around. It was just passing through. It had entered our solar system from one direction, and it was destined to exit in another, never to return. For the first time in history, we had incontrovertible proof we had a guest from another star. It was a profound, humbling moment. The emptiness between the stars was not empty at all. It was a highway, and objects from other solar systems were traveling it. We had just never seen one before. We scrambled to observe it, this messenger, from a place we could not imagine. It was given a name fitting its significance, Oumuamua, a Hawaiian word, meaning a scout or a messenger from afar arriving first. But the more we looked at this celestial scout, the less sense it made. It defied every category we had. As it whipped around the sun, it should have behaved like a comet. The intense solar heating should have caused ices to sublimate, creating a visible coma and a tail. Yet Oumuamua showed nothing. Our most powerful telescopes saw only a point of light, a bare, inert object with no hint of the gaseous shroud that defines a comet. So perhaps it was an asteroid, a dry chunk of rock from another star system. That seemed plausible, but its other characteristics were deeply strange, bordering on the impossible. The way its brightness flickered was extreme. The light curve, the graph of its changing luminosity, suggested an object with a bizarre, elongated shape unlike any known asteroid. It was at least 10 times as long, as it was wide, tumbling end over end through space. Was it a cosmic cigar, a celestial needle, or perhaps a flattened, pancake-like shard? No one knew for sure. We were trying to understand a visitor from a place with different rules, a different history. We were trying to translate a message written in a language we had never encountered. And then came the final baffling mystery. As Oumuamua began its departure, speeding away from the sun and back toward the interstellar void, astronomers tracking its path noticed something subtle but undeniable. It was accelerating. It was moving away faster than gravity alone could explain. Some gentle, persistent force was giving it an extra push. For a comet, this would be perfectly normal. The outgassing of jets of gas and dust from its surface acts like a set of tiny rocket thrusters altering its course. But Oumuamua had no visible outgassing, no coma, no tail. What then was pushing it? The question ignited a firestorm of debate and speculation. Was it an exotic object we had never theorized? Perhaps an iceberg made of pure hydrogen or solid nitrogen, whose outgassing would be invisible to our telescopes? Or was it, as some reputable scientists dared to suggest, something else entirely? Could the slight persistent push be the pressure of sunlight on an object that was incredibly thin and light? Was it possible we had just witnessed the passage of a piece of extraterrestrial technology, a naturalistic light sail? Or a derelict probe from a long-dead civilization? We will likely never know. Oumuamua was gone as quickly as it came, a fleeting, ghostly encounter that left us with more questions than answers. It was a tantalizing glimpse into the wider galaxy, a confirmation that we are part of a much larger, more populated cosmos. But it also left a void. We had seen a messenger, but we couldn't read the message. The scientific community was left hungry, desperate for another chance. We needed another visitor, one we could study in more detail, one that hopefully would play by the rules. The wait was not long. The age of great surveys had dawned. All over the world, robotic eyes now scan the sky every single night, mapping the celestial traffic with unprecedented precision. Among them is the Asteroid Terrestrial Impact Last Alert System, or ATLAS, a set of telescopes in Hawaii, Chile, and South Africa. Its primary mission is to protect us, to find any incoming space rocks on a collision course with Earth. But in its tireless nightly vigil, ATLAS sees everything that moves against the backdrop of the stars, and in early 2023, its sophisticated software flagged an object of interest. At first glance, it was unremarkable, just another faint smudge moving through the outer solar system. It was given the provisional designation C, 2023 A3, the C, indicating that it was a comet, likely on a long-period orbit. But as more observations poured in from around the world and its trajectory was refined, a jolt of electricity shot through the astronomical community. The calculations showed that this was no returning member of our solar family. Its orbit was hyperbolic. It was another traveler from the interstellar deep. The excitement was palpable, a feeling of imminent revelation. This could be the one. This could be our Rosetta Stone, the object that would finally unlock the secrets that Oumuamua had only hinted at. Unlike the strange, inert Oumuamua, this new visitor seemed comfortingly familiar. In the early observations, it presented a faint but distinct coma. It looked for all the world like a proper comet. A wave of relief and anticipation swept through observatories globally. This was the opportunity we had been dreaming of. A chance to study a genuine, bona fide interstellar comet, a dirty snowball from another star. Imagine what it could tell us. By analyzing the light filtering through its coma, we could determine its chemical composition with extraordinary detail. We could compare the building blocks of another solar system to our own. Would we find the same ratios of water, of carbon, of organic molecules? Would we discover that the ingredients for life are common throughout the galaxy, delivered by comets, just as they may have been delivered to a young Earth? Or would we find a chemistry so alien, so different from our own, that it would force us to rethink the very processes of planetary formation? The possibilities were dizzying. This object wasn't just a scientific curiosity. It was a chance to glimpse our own cosmic origins in a distant mirror. The International Astronomical Union soon made it official. Its designation was changed to 3I, Atlas. The I, proudly announcing its interstellar heritage, only the third such object ever to be confirmed. The world's telescopes, both on the ground and in space, turned their gaze toward it, preparing to witness the story of another star system as it unfurled in our own backyard. We thought we were finally getting the answers we craved. We believed 3I, Atlas, was the simple, straightforward messenger we had been waiting for, a celestial sibling to our own comets here, to tell us that we are not so different after all. The narrative felt clean, satisfying. Oumuamua was the anomaly, the freak. 3I, Atlas, was the norm, the baseline. But the universe is rarely so simple. It delights in subverting our expectations, in peeling back one layer of mystery, only to reveal an even more profound one beneath. Even in those first few months of observation, as 3I, Atlas, continued its majestic silent fall toward our sun, subtle clues began to emerge from the data, faint whispers in the mathematics of its orbit, and the character of its light suggested that this visitor was not what it seemed. Its behavior was not quite right. The story we were preparing to tell, the story of a familiar comet from an unfamiliar place, was already beginning to fray at the edges. We were on the verge of a discovery far stranger and far more significant than we could have ever imagined. We thought we were looking at a ghost from another star. We were about to realize we were looking at something else entirely. Its journey inwards was at first a textbook case of cosmic pilgrimage. For months, 3I, Atlas, adhered to the gravitational script written for it by the sun, its path, a graceful, predictable arc. Every observatory capable of turning its eye towards the traveler did so, eager to chart the slow awakening of this visitor from the void. We watched, expecting the familiar stirrings of a long-frozen comet as it felt the first tentative warmth of our star. We anticipated the gentle sigh of sublimating ice, the slow unfurling of a tail that would paint a temporary streak across the ancient celestial canvas. The universe, it seemed, was about to perform a familiar, beloved play. But 3I, Atlas, was not following the script. It was rewriting it. The first hint of its profound strangeness was a whisper in the data, a subtle anomaly in the numbers that stream back from the cold eyes of telescopes. It was getting brighter. This in itself was not unusual. It is what comets do. As they fall toward the sun's furnace, their surfaces warm, and ancient ices, water, carbon dioxide, ammonia transform directly into gas, a process we call sublimation. This expanding shroud of gas and dust, the coma, catches the sunlight and begins to glow, making the comet appear brighter. But Atlas's brightening was different. It was unnervingly rapid, almost violent in its acceleration. Where other comets gradually awakened, this interstellar guest was roaring to life. Its light curve, the clinical graph of its luminosity over time, was not a gentle slope, but a near vertical spike. It was as if we were watching a distant campfire, inexplicably erupt into the searing intensity of a magnesium flare. Astronomers around the world conferred their digital forums, buzzing with theories. Perhaps our initial estimates of its size were wrong. Maybe this wasn't a modest traveler a few kilometers across, but a behemoth, a colossal iceberg from interstellar space, with a vast surface area now being superheated by the sunday. This hypothesis was tantalizing, suggesting we were witnessing the arrival of a truly monumental object from another star. Others proposed a more dynamic explanation. Perhaps its surface was unusually rich in hypervolatile ices, substances like frozen nitrogen or carbon monoxide, which boil away at far lower temperatures than water ice. Under this model, Atlas was shedding its outer layers at a ferocious rate, a celestial onion peeling itself under the sun's gaze. For a time, these explanations felt adequate, if a little strained. They allowed us to place this strange new object within the comfortable confines of what we thought we knew. The universe was presenting a puzzle, certainly, but one we believed we had the pieces to solve. The spike in brightness was just the prelude, we told ourselves, to a truly spectacular cometary display, one that might even become visible to the naked eye. We were preparing for a celestial celebration. Instead, we became witnesses to a disintegration. It happened without warning. One night in early April, the steady, albeit intense, point of light that had been 3i, Atlas, was gone. In its place there was something else, something fractured. The initial observations from ground-based telescopes were confusing, the images blurred by Earth's turbulent atmosphere, but they hinted at a horrifying transformation. The core, the solid nucleus we had been tracking so diligently, had broken apart. This was the moment the world's premier astronomical instrument, the Hubble Space Telescope, was turned upon the scene. Floating high above the distortion of our world, Hubble delivered an image of shocking crystalline clarity. It was a vision of cosmic ruin. Where there had been a single star-like object, Hubble revealed a ghostly flotilla of at least 4 distinct fragments, drifting apart like the wreckage of a sunken ship. They were shrouded in a shared, diaphanous cloud of their own debris, a funeral shroud marking the place where a solid world had moments before existed. The news rippled through the scientific community, not with celebration, but with a stunned, profound sense of bewilderment. Comets do on occasion break apart. The delicate dance of gravity and thermal stress can be too much for these loose conglomerates of ice and rock. But the disintegration of 3i Atlas was unlike any we had ever documented. It was not a clean split into 2 or 3 large pieces, the typical fate of a comet under gravitational strain from the sun or a giant planet. Nor was it the gentle fizzling out of a comet that had simply exhausted its volatiles. This was a catastrophic, almost explosive failure of its entire structure. Follow-up observations in the days that followed only deepened the enigma. Hubble watched as those initial 4 pieces themselves began to crumble, splintering into dozens of smaller, fainter fragments. The scene transformed from a simple breakup into a complete cascading collapse. We were watching a world dissolve. The intense brightening we had mistaken for a sign of spectacular life was, in retrospect, its death rattle. It was the furious final outgassing of a body tearing itself apart from the inside out, a scream of light before it shattered into silence. With the spectacle of its destruction laid bare, the real work began. The central question was no longer what it was doing, but times why asterisk. Why did this interstellar visitor, which had survived a journey of millions, perhaps billions of years through the cold, empty darkness between the stars, choose to disintegrate so completely upon arriving in our home? Scientists fell back on their trusted models, the theoretical frameworks built upon the observation of thousands of comets from our own solar system. The first and most obvious culprit was thermal stress. Imagine taking a frozen rock from the absolute zero of deep space and placing it under the heat of a celestial blowtorch. The surface expands rapidly, while the core remains frigidly cold. This immense temperature gradient can induce powerful stresses, creating fissures that can propagate through the entire body, cracking it like an ice cube in warm water. This model works beautifully for many comets that venture close to the Sunday. But for 3I, Atlas, the numbers refuse to align. Its fragmentation began when it was still more than 150 million kilometers from the Sun, farther than the Earth's own orbit. At this distance, the Sun's warmth is significant, but it is not the overwhelming furnace one finds closer in, where thermal shock is a more common executioner. The solar heating it was experiencing should have been endurable, especially for an object that had presumably survived whatever cataclysm hurled it from its native star system. The thermal stress model predicted cracks and fissures, perhaps a piece breaking off. It did not predict this wholesale cascading demolition. The explanation felt thin, an ill-fitting patch on a gaping hole in our understanding. The next theory centered on rotation. Many small bodies in the solar system are not static spheres, but spinning irregular shapes. As sunlight strikes their surfaces, it doesn't just heat them. It imparts a tiny, almost infinitesimal amount of momentum. Over millennia, these gentle photon nudges can accumulate, causing the object to spin faster and faster. We call this the Yo-epi effect. If an object is a loosely bound pile of rubble, as many comets are believed to be, this increasing centrifugal force can eventually overcome its own feeble gravity. It becomes a gravitational gyroscope, spinning out of control, flinging material from its equator until it tears itself to pieces. Could this be what happened to 3I, Atlas? Did its long interstellar voyage leave it in a precarious, rapidly spinning state? And was the final push from our Sun all that was needed to send it over the edge? The idea was elegant, a silent, graceful mechanism for self-destruction. Yet again, however, the data offered a stubborn rebuttal. For the Yorp effect to be this dramatically effective, Atlas would have needed to have a highly irregular, almost propeller-like shape and be spinning at a dizzying rate. Furthermore, a rotational breakup typically scatters debris in a specific planar fashion flung outwards from the equator. The fragments of 3I, Atlas, however, were separating from each other, with very low velocities, drifting apart gently in a three-dimensional cloud. Their languid separation did not match the violence of a body spinning itself into oblivion. The evidence for a rotational breakup was simply not there. The celestial gyroscope theory, as compelling as it was, spun down to a halt. With the two primary external mechanisms proving inadequate, astronomers turned their focus inward to the very heart of the object itself. Perhaps the destroyer of 3I, Atlas, was not the Sun but the comet itself. This theory posited the existence of a cosmic depth charge buried deep within its core. We know that comets can contain pockets of extremely volatile ices, like the carbon monoxide we had speculated about earlier. These substances can remain stable in the deep freeze of space, but as the comet warms, they can sublimate explosively within their subterranean chambers. If a large pocket of this super-volatile ice were to suddenly flash into gas beneath the surface, the immense pressure could overwhelm the structural integrity of the nucleus, blowing it apart from the inside. This violent outburst model seemed at last to fit the visual evidence. It could explain the dramatic brightening as a precursor event, the venting of gas through surface cracks just before the final cataclysm. It could also account for the low separation velocity of the fragments, which would be pushed apart by the expanding gas cloud rather than flung by rotation. For a moment, it felt like a breakthrough. We had found a plausible narrative for this bizarre celestial death. But even this, the most promising of the conventional models, began to fray at the edges. The sheer scale of the disintegration remained a sticking point. For an internal explosion to shatter a body several kilometers wide so thoroughly, the energy required would have to be colossal. It would necessitate a very large, very deeply buried, and very specific type of volatile pocket, an architecture that seemed almost too perfectly engineered for destruction. Moreover, the behavior of the fragments, times after times the breakup, was perplexing. They did not simply drift and fade as inert chunks of rock and ice should. Some of them continued to brighten and dim sporadically, suggesting they were still active, still outgassing, still behaving like miniature independent comets. A simple explosion model couldn't easily account for this sustained complex activity among the debris field. The cosmic depth charge theory was the best we had, but it felt incomplete, a story missing its crucial final chapter. Every attempt to impose our understanding of comets onto this object was failing. The intellectual scaffolding, built over centuries of observation, was collapsing. We were trying to fit a key forged in another star system into a familiar lock, and the tumblers simply refused to turn. A profound realization began to dawn across the astronomical world. The problem might not be with our models of cometary destruction. The problem might be with our initial assumption that 3I, Atlas, was a comet at all. We had classified it based on its appearance from a great distance, a fuzzy object with a tail following a path from interstellar space. But as it drew closer, it had systematically violated every expectation we had for such a body. Its brightening was anomalous. Its method of disintegration was unprecedented. Its post-breakup behavior was baffling. It wore the disguise of a comet, but its true identity was something else entirely. The fragments, once seen as mere debris, now took on a new significance. They were not just the wreckage of a dead object. They were clues, pieces of an alien jigsaw puzzle scattered across our sky. The catastrophic end of 3I Atlas was not in fact an end. It was a revelation. By breaking apart, it had given us an accidental, intimate glimpse into its internal structure, a view we would never have otherwise had. Its heart was now exposed. And as we trained our most powerful instruments on these spectral remains, we prepared to see the core of an interstellar visitor for the first time. We were about to look inside a messenger from another star, expecting to find the familiar heart of a comet. What we would find instead would challenge the very definition of what an object drifting between the stars could be. And so the beautiful ephemeral ghost that had haunted our skies for months was gone. What remained was not a tragedy, but an unprecedented invitation. The cataclysm that had torn 3I Atlas apart, that violent incandescent dissolution, had in a single brutal act accomplished what no space mission ever could. It had performed a cosmic autopsy, cracking open the interstellar traveler and spilling its innermost secrets across the void for us to see. The disappointment among astronomers was palpable, but it was swiftly replaced by a dawning, electrifying realization: the death of the comet was the birth of an entirely new field of inquiry. This was a gift, a fleeting window into the heart of a messenger from another star. A quiet, frantic race against time began. The fragments, once a cohesive nucleus, were now a dispersing cloud of cosmic shrapnel, each piece on its own trajectory, drifting further apart with every passing hour. Observatories across the globe turned their monolithic eyes toward the celestial crime scene, but one instrument held the promise of the clearest view. Floating high above the distorting veil of our atmosphere, the Hubble Space Telescope, our steadfast sentinel in the dark, was redirected, its mission to stare unblinking into the wreckage and read the story written there. This was no longer about admiring a comet's majestic coma and tail. This was about interrogating the survivors, the core witnesses to its true nature. The light from these tiny tumbling pieces of a distant solar system was fantastically faint, a cascade of dying embers against the infinite black. Only Hubble possessed the precision and the patience to capture it. The first line of questioning relied on a beautifully simple principle, watching how the fragments twinkled. This technique, known as light curve analysis, is the astronomer's oldest trick. It is the art of measuring an object's brightness over time. For a spinning, irregularly shaped body, the amount of light it reflects back to us changes as different faces, some large and bright, some small and shadowed, rotate into view. By plotting these subtle fluctuations, you can deduce an object's shape and its spin, creating a rudimentary model of a thing you can never hope to touch. It's like trying to understand the shape of a spinning diamond in a dark room by observing only the glints of light it casts upon a distant wall. The science team had a clear expectation of what they should see. Fragments from a conventional comet's nucleus are notoriously unruly. They are not solid, uniform objects. They are fragile conglomerates of ice, rock, and dust, often called dirty snowballs. As these pieces tumble through space, warmed by the sun, their surfaces don't just reflect light, they erupt. Pockets of frozen gas, water, carbon monoxide, carbon dioxide sublimate, explosively blasting away jets of dust and vapor in unpredictable bursts. This outgassing creates a chaotic flickering light signature. The light curve of a typical cometary fragment should look like the frantic scribbling of a seismograph during a major earthquake, a jagged, unpredictable line of sharp peaks and deep troughs. It would be the signature of something dynamic, violent, and unstable. This is what theory predicted. This is what decades of observing our own solar system's comets had taught us to anticipate. Hubble began its long stare, its sensitive photometers, gathering photons one by one, accumulating the faint whispers of light from the heart of 3I, Atlas. The first data trickled back to Earth, painting a picture that was at first confusing. Then, as more observations were compiled, the confusion solidified into profound astonishment. The light curves from the largest fragments were not chaotic. They were not the violent sputtering signatures of sublimating ice. Instead, they were smooth, rhythmic, almost elegantly predictable. The fragments were pulsing with a steady metronomic beat. Their brightness rose and fell with a clockwork regularity that was utterly alien to the concept of a disintegrating icy body. It was the signature of a solid object, or a collection of solid objects, tumbling through space with a stable, well-defined rotation. There were no sudden violent jets of gas throwing off the rhythm. There was no erratic flickering from explosive pockets of ice. It was as if we were watching not the embers of a dying firework, but the steady, graceful spin of a shard of polished stone. This was the first profound crack in the cometary hypothesis. The evidence suggested these pieces were not fluffy, porous aggregates of ice and dust, but something far more cohesive, more structurally sound. They were behaving like tiny asteroids, not chunks of a disintegrating snowball. The models derived from these hypnotic rhythmic pulses painted a picture of elongated shard-like fragments. They weren't crumbly clumps. They were definite solid shapes holding their form, even under the relentless pressure of the sun. This initial finding sent a shockwave through the observation teams. If the object's physical behavior was so fundamentally different from a comet's, then what about its chemical composition? The light curve had provided the first clue that 3I, Atlas, was wearing a disguise. The next tool would strip that disguise away entirely. Science now turned to its most powerful decoder ring spectroscopy. If photometry is about times, how much times light an object reflects, spectroscopy is about times, what kind times of light it reflects. By passing the faint light from the fragments through a prism-like instrument, astronomers can spread it out into a rainbow, a spectrum. But this cosmic rainbow is not perfect. It is scarred, with dark, narrow lines, missing slivers of color that have been absorbed by specific chemical elements and compounds present on the object's surface or in the gas surrounding it. Each element, each molecule has a unique and unchangeable spectral barcode. Find the barcode for water, and you have found water. Find the barcode for cyanogen, a carbon-nitrogen molecule, and you have found the unambiguous, universally accepted smoking gun of a comet. Cyanogen gas is a hallmark of cometary comas, a chemical signature so reliable that its presence is practically the definition of a comet. Hubble's spectrographs were trained on the ghostly wisps of gas and dust that still clung to the largest, most coherent fragments. This was the moment of truth. The expectation was clear: the spectrum should have been rich with these telltale signatures. We should have seen the deep absorption bands of water ice, the chemical fingerprint of the very substance that was supposed to be driving this entire spectacle. We should have seen the sharp, clear lines of carbon monoxide and carbon dioxide, the frozen gases that power the dramatic jets on other comets. And above all, we should have been greeted by the familiar, comforting signal of cyanogen. This would have confirmed that 3I, Atlas, despite its structural peculiarities, was at its heart a member of the cometary family. It would have been a strange cousin, perhaps, but a cousin nonetheless. The data streamed from orbit was processed, calibrated, and finally displayed on screens in control rooms and university offices around the world. And a stunned silence fell. There was nothing. The space in the spectrum where the strong characteristic barcode for water ice should have been was eerily, unnervingly blank. The region where the vibrant signatures of other key volatile gases were expected to appear showed only a flat, featureless line. And most damning of all, the hunt for cyanogen, the definitive test, came up completely empty. There was no trace of it, not a whisper. The cometary smoking gun wasn't just missing. It was as if the gun had never existed. The implications were staggering, almost unbelievable. Scientists checked their instruments. They reran their calibrations. They scrutinized every step of the data processing pipeline, searching for a mistake, an error that could explain this impossible result. But there was no error. The data was pristine, the conclusion unambiguous. The material breaking off from the core of 3I, Atlas, was not releasing significant amounts of water vapor or any other volatile gas. The very engine that defines a comet, the sublimation of ice into gas that creates the coma and tail, was simply not there. The beautiful, expansive cloak of gas and dust that had made 3I Atlas look so much like a comet must have been produced by a minuscule amount of hyper-volatile ice on its surface, perhaps a substance like frozen carbon monoxide, which can vaporize much farther from the sunday. It was a thin, superficial layer, a fleeting costume. Once that thin veneer burned away, the true nature of the object beneath was exposed. And that nature was nothing like a comet. So what times did the spectrum show? It revealed a dull, nearly featureless reflection of sunlight, consistent with a dark, rocky material, something akin to the carbonaceous asteroids found in the outer belts of our own solar system. Furthermore, the dust that times was, times present, was spectrally different from typical cometary dust. Cometary dust is usually reddish, rich in organic molecules. The dust from 3I Atlas was more neutral in color, suggesting a composition dominated not by organics and ice, but by silicates, by rock. Every single piece of evidence from two independent and powerful methods was now pointing in the same revolutionary direction. The steady, rhythmic pulse of the light curves spoke of a solid, cohesive body. The stark, empty silence of the spectra spoke of a profound lack of ice and gas. The final piece of the puzzle was density. A comet's nucleus is a famously light and fluffy thing, often less dense than powdered snow, barely held together by its own feeble gravity. It is a meringue in the cosmic oven of the sun, designed to puff up and disintegrate. But the fragments of 3I Atlas defied this. The way they held together, even as they broke apart, and the speed at which they separated allowed astronomers to place rough constraints on their mass and density. The numbers that came back were once again completely at odds with the cometary model. These pieces were dense, perhaps 2 or 3 times denser than water. They were not cosmic meringues, they were celestial stones. They behaved not like loosely packed snowballs, but like chunks of solid rock, or perhaps something even more robust. The possibility, once unthinkable now, had to be seriously considered. Could these fragments contain not just rock, but metal? The case was closed. The verdict was in. The assumptions that had guided our understanding of this visitor for over a year were not just incorrect, they were profoundly, fundamentally wrong. 3I, Atlas, was not a comet. It had masqueraded as one putting on a spectacular, but ultimately deceptive show. Its approach to our sun was not the homecoming of a familiar type of object, but the arrival of something genuinely new, something for which we had no category. The fragmentation, which we first saw as the tragic end of a beautiful object, was in fact the climax of a cosmic play the moment the mask was finally removed. Beneath the ghostly costume of gas and dust, we found a body of stone, a dark, dense, and ancient artifact from a planetary system utterly unlike our own. We had reached out hoping to shake hands with a distant cousin of Halley's Comet, only to find ourselves face to face with a complete and utter stranger. The revelation was not an ending, but a new, more difficult beginning. It shattered our simple classification system and forced us to confront our own ignorance. It replaced a comfortable answer with a cascade of bewildering questions. If this object wasn't born in an icy cloud at the edge of its star system like a comet, then where did it come from? What kind of solar system forges bodies of rock and then ejects them into the interstellar darkness? Was 3I, Atlas, a piece of something larger, a fragment of a shattered exoplanet, a tiny wandering moon torn from its orbit, or something else entirely? The debris field of our interstellar visitor was no longer just a subject for astronomical observation. It had become a philosophical challenge. It was a stark reminder that the universe is not obligated to conform to our expectations. The pieces of 3I, Atlas, now tumbling silently into the outer darkness, had delivered their testimony. And in doing so, they had not solved a mystery, but had bequeathed to us a far deeper and infinitely more compelling one. The silence in control rooms around the world was a sound all its own. Not an absence of noise, but a presence, a heavy electric stillness filled with the weight of a paradigm shattering. For days, for weeks, the data had trickled in, each packet of information, a brushstroke on a canvas we thought we understood. We were painting a portrait of a comet familiar and predictable. Then the final piercing observation from the orbital interferometers cut through the noise, resolving the core. And the portrait was revealed to be a monster, or a miracle. No one was yet sure which. That single crystalline image of a dense metallic and utterly uncomet-like heart did more than just surprise us. It invalidated entire careers' worth of assumptions. It had taken our tidy celestial catalogue with its neat boxes for comets, asteroids, and planetoids and set it on fire. The ghost we had been chasing through the void was not a phantom of ice and dust. It was a ghost made of iron and nickel, a shard of something solid, ancient, and impossibly foreign. And so the frantic scramble began. Digital conference rooms buzzed at all hours. Whiteboards filled with equations that were immediately erased. And 1,000 new simulations were born only to die, moments later, unable to reconcile the object's bizarre outgassing with its dense, rocky nature. The discovery of the core hadn't provided an answer. It had annihilated the question itself, replacing it with a dozen more, each more profound than the last. If 3I, Atlas, wasn't a comet, what in the cosmos was it? The first and most breathtaking hypothesis to gain traction was one of unimaginable violence. We might be looking, astronomers proposed, at a message in a bottle from a shipwreck, the shipwreck of a planet. Imagine not in our solar system, but in another, light years away and eons ago, a planetary system in the turbulent throes of its adolescence. Much like our own chaotic youth, this was a time of celestial billiards, with worlds weaving and jostling for gravitational dominance. Here, a young planet was forming a super-Earth, perhaps 5 or 10 times the mass of our own world. It was building itself layer by layer, differentiating into a dense metallic core, a molten silicate mantle, and a burgeoning crust. It was a planetary embryo on the verge of becoming a stable, mature world, but it never got the chance. In this brutal cosmic ballet, its path intersected with that of a migrating gas giant, a Jupiter on the move, or perhaps it was caught in the gravitational crossfire of a binary star system. The encounter was not a gentle nudge. It was a cataclysm of physics-defying proportions. The gravitational tidal forces exerted on the smaller world were titanic, stretching and warping it, peeling back its lighter outer layers, the crust and the mantle, like the skin of an orange. This process, known as tidal stripping, is one of the most destructive forces in the universe. We see its effects in shredded stars orbiting black holes, but to imagine it happening to a nascent planet is to conjure a truly hellish vision. The very substance of the world was torn away, blasted into superheated dust and gas, leaving only the most gravitationally bound part of it intact, its core. An exposed, naked planetary heart of iron, nickel, and other heavy elements, glowing with the residual heat of its calamitous birth and violent unmaking. And then came the final act of this tragedy, the ejection. Having had its soul stripped bare, the surviving core was now on an unstable slingshot trajectory. The same gravitational behemoth that had destroyed it now acted as a cosmic catapult, flinging the remnant out of its home system entirely. It was launched into the lonely interstellar dark at a velocity our own spacecraft can only dream of. For millions, perhaps billions of years, it has wandered, a silent, dark traveler cooling slowly as it tumbled through the void. This theory was intoxicating because it explained the core's most shocking features, its incredible density and its metallic composition. It was quite literally the stillborn heart of a world that never was. The models were run and rerun. A core fragment of a super-Earth ejected after a brutal tidal stripping could indeed match the mass, the density, and the trajectory of 3I Atlas almost perfectly. It was a coherent, terrifyingly elegant narrative, but like all grand stories, it had a complication, a fatal flaw perhaps: the outgassing. If this object was a planetary core forged in the incandescent heat of planetary formation and then violently stripped, it should be bone dry. Any volatile ices like water or carbon dioxide would have been vaporized in its fiery genesis. It should be a dead rock, an inert cannonball. Yet 3I, Atlas, was undeniably active. It was shedding gas and dust, creating the very coma that had led us to mistake it for a comet in the first place. Where did this ice come from? Proponents of the planetary fragment hypothesis were forced to add a second chapter to their story. Perhaps, they argued, during its long pilgrimage through interstellar space, the core passed through a dense molecular cloud, a stellar nursery rich in frozen gases and dust. Over thousands of years, a thin, frosty patina of ice and organics could have condensed onto its cold metallic surface. It would have been like a piece of metal left out on a winter's night, accumulating a layer of frost. This interstellar frost, just a few meters thick, would be all it took. As 3I Atlas approached our sun, the rising temperatures would sublimate this thin foreign veneer, producing the observed outgassing, without requiring the object itself to be an icy comet. It was a clever addendum, a patch on the theory, but it also felt convenient. A story layered on top of a story, and for many scientists that complexity was a red flag. The universe often prefers simpler, more direct answers. This dissatisfaction led a second camp of researchers to a different, less violent, and perhaps more profound conclusion. What if 3I Atlas wasn't the remnant of something destroyed, but a pristine example of something entirely new? What if it wasn't a fragment at all, but a whole primordial object born in the interstellar dark and representative of a completely different path of planetary formation. They proposed we were looking at a new class of object, a dense rock and metal, interstellar asteroid that had formed with ice trapped inside it from the very beginning. This wasn't Oumuamua's cousin. Oumuamua was thought to be a dry, rocky body behaving as expected. 3I Atlas was something else entirely. It was a hybrid, a chimera that breaks the fundamental divide in our own solar system between the rocky bodies of the inner system and the icy bodies of the outer. To understand this, we have to let go of our sun-centric biases. Our solar system formed with a specific chemical gradient. It was hot near the sun, so only rock and metal could condense. Far from the sun, beyond a boundary we call the frost line, it was cold enough for water, ammonia, and methane to freeze into ice. This is why we have rocky planets close in and gas and ice giants far out. But who says every star system must follow this exact blueprint? Imagine a star system that formed from a molecular cloud, unusually rich in heavy elements, metals, forged in the death of an earlier generation of massive stars. In the protoplanetary disk of such a system, metallic and silicate grains would be far more abundant everywhere. It's conceivable that large, dense planetesimals, the building blocks of planets, could form far out in the cold regions, incorporating vast quantities of water ice directly into their metallic rocky matrix. Think of it not as a rocky core with a layer of frost on top, but as a kind of cosmic concrete where ice is the aggregate mixed intimately with a cement of iron and silicate. Such an object would be incredibly dense, just like 3I Atlas, and it would be packed with volatiles. As this iron iceberg was eventually ejected from its own system through the routine gravitational nudges of its larger planetary siblings, it would carry its frozen water deep within its core. Then, upon entering our solar system, the sun's warmth would begin to penetrate. Metal is an excellent conductor of heat. Unlike a normal comet where the sun bakes off the surface layers, the heat would travel deep into the body of 3I Atlas, reaching the embedded ice pockets. The ice would sublimate into gas-building pressure until it burst forth through fissures in the rocky exterior. This would perfectly explain the intermittent jet-like outgassing we observed, not a steady plume from a melting surface, but violent episodic releases from a deep internal reservoir. This theory offered a breathtaking glimpse into the sheer diversity of the galaxy. It suggested that other solar systems might not be simple variations of our own, but might follow entirely different rules of construction, creating objects we have no analog for. 3I Atlas, in this view, was not a cosmic refugee from a planetary war, but an interstellar ambassador, bringing us the blueprint of a world built on principles alien to our own. It was a pristine relic from a different kind of creation story. It was a powerful and compelling alternative, one that seemed to fit the dual nature of our visitor, dense as a rock yet active as a comet more naturally. It required no extra stories, no convenient frost layers accumulated in deep space. The object was simply what it was from the moment of its birth. But the universe is rarely content with just two possibilities. Its capacity for the strange, the exotic, and the utterly unforeseen is practically infinite. And so a third set of hypotheses began to bubble up from the fringes of theoretical astrophysics ideas that pushed the boundaries of what we thought was even possible. Even the story of an iron iceberg from a metal-rich system felt to some too familiar. It was still using the basic ingredients of planets as we know them. What if the forge that created 3I Atlas was a place of such extreme physics that it operates outside the normal rules of star and planet formation altogether? One of the most exotic proposals pointed to one of the most violent events imaginable: the merger of two neutron stars. When these city-sized hyperdense stellar corpses collide, they create a kilonova, a cataclysm that outshines entire galaxies for a brief moment. It is in this cosmic crucible, this particle accelerator of the gods, that the universe forges the heaviest elements: gold, platinum, uranium. The explosion blasts this exotic material across space. Could 3I Atlas be a droplet of this cooling radioactive slag, a nugget of pure neutron star-forged matter ejected and sent tumbling through the cosmos? The density would be off the charts, and its composition would be unlike anything we've ever seen. While initial calculations suggested 3I Atlas wasn't times that times dense, the sheer audacity of the idea stretched the minds of the entire community, forcing them to consider origins far beyond a simple protoplanetary disk. Another, perhaps more plausible, exotic theory looked not to a world's death but to its transformation. It centered on a theoretical class of planet known as a Chthonian planet. This isn't a world destroyed by a collision, but one that is slowly, relentlessly unmade by its own star. Imagine a gas giant, a hot Jupiter, orbiting perilously close to its parent sun. The star's ferocious stellar wind and searing radiation act like a celestial blowtorch, heating the planet's atmosphere to thousands of degrees and stripping it away molecule by molecule over millions of years. This process of hydrodynamic escape would eventually scour the planet of its entire gaseous envelope, leaving behind only the dense, rocky or metallic core that once lay at its center. This exposed core, a Chthonian planet, would be a testament to stellar tyranny. If this stellar remnant were then ejected from its system, perhaps by a complex three-body interaction, it would perfectly match the description of a dense, formerly superheated core. And crucially, unlike the planetary collision model, this slow-bake method might allow some deeply buried, highly pressurized water that was part of the core's original formation, to remain locked inside. This offered a potential solution to the nagging problem of the outgassing, blending the exposed core idea with the internal reservoir model. The competing theories laid bare a fundamental truth: we were adrift in a sea of stunning possibilities, each with its own profound implications. Was our visitor a mourner, the heart of a murdered world, telling a tale of gravitational violence and destruction? Was it a messenger, a pristine building block from a system with a chemistry so different from ours that it challenges our very dollars definition of what a planet is? Or was it something truly alien, a creature born of fire and forces we can barely comprehend? A relic from a neutron star's ghost, or a world flayed by its own parent star? The revelation of the core had not closed the book on 3I Atlas. It had thrown it wide open, revealing hundreds of blank pages. We now knew what it was, times not asterisk. It was not a comet, but in its place, a void of knowledge had appeared, and into that void rushed the full creative and sometimes terrifying imagination of science. 3I Atlas was no longer just an interstellar object. It had become a mirror reflecting our own ignorance, but also our boundless curiosity. It created a classification crisis, demanding a new name, a new category, a new understanding of the universe's potential. The race was no longer just about tracking its path through our system. The race was now to decode its identity, to choose one of these incredible stories, or write an entirely new one before it disappeared back into the darkness, taking its secrets with it forever. The challenge was set, the theories were on the table. Now the hunt for proof, for the one piece of evidence that could turn science fiction into scientific fact, was about to begin, undefined. And so we stand at a precipice of understanding, staring into a chasm of contradictions. The accumulated data, gathered from every vigil-keeping telescope on Earth, paints a portrait of an object that simply should not exist. Before us lie the scattered pieces of a puzzle that defy every known picture. We have tracked its path, a lonely trajectory cutting across the interstellar void, confirming its origin far beyond the frontiers of our own solar system. We have watched it, a faint speck against the infinite, begin to glow, not with the brilliant transient flare of a comet awakening, but with the steady, ghostly aura of something else entirely. We have seen it fracture, breaking apart, under a thermal strain so gentle it would barely warm your hand, suggesting a fragility that borders on the impossible. This celestial voyager, this 3I, Atlas, possessed a core, a heart of stony metallic matter, yet it wore the dusty shroud of a comet. It was a contradiction made manifest, a cosmic riddle sent to challenge the very foundations of what we thought we knew about the universe's travelers. For generations, our expectations were shaped by a simple, elegant logic. The cold, dark expanse between the stars is a realm of profound frost. Any object cast out from its home system, sentenced to wander for millions or even billions of years, would surely be a creature of ice. It would be a primordial snowball, a relic from the outer edges of a distant solar nebula, where volatiles like water, carbon monoxide, and methane could freeze solid. These interstellar comets, like the one discovered by Gennady Borisov, were the ambassadors we anticipated. They would arrive, be warmed by our sun, and their ices would sublimate into vast, magnificent comas and tales of familiar and spectacular greeting card from a neighboring star. This was the paradigm. It was clean, it was predictable, and 3I, Atlas, rendered it utterly obsolete. The spectrographs, our most powerful tools for chemical interrogation, returned a verdict that was both stunning and unequivocal. We searched for the chemical fingerprint of water, the signature of hydroxyl radicals liberated by sunlight, and we found nothing. We hunted for the telltale signs of carbon-based gases, the very breath of a comet, and there was only silence. The object's core was fundamentally rocky, rich in the same silicates and perhaps even ferrous metals that constitute the planets and asteroids of our own inner solar system. Yet it was undeniably active. It was shedding mass, creating a vast, diffuse cloud of dust that mimicked a cometary coma with haunting precision. Here, then, was the central paradox, the scientific koan that kept astronomers sleepless. How does a rock, an inert piece of celestial stone, generate a coma? An asteroid does not sublimate. It does not erupt under the distant sun's gentle influence. It simply travels a silent, passive wanderer. To behave as 3I, Atlas did a rock would need an engine, a mechanism to violently expel its own substance into space. But without the phase transition of ice turning to gas, the known engine of all cometary activity, there was no conceivable source of power. It was like discovering a shipwreck in the deep ocean with its sails impossibly full, billowing with a wind that did not exist. We were forced to confront a revolutionary possibility, that we were not looking at a primordial object at all, but at something far stranger and perhaps far more significant. We were not seeing a cosmic snowball, but a piece of cosmic shrapnel. The first models to emerge from this intellectual crisis were attempts to salvage the old ideas, to stretch them to their breaking points. Perhaps some argued 3I, Atlas, was an exotic, desiccated husk, a comet that had made so many fiery passages around its parent star that its surface had been baked dry, leaving only a rocky crust. In this scenario, heat from our sun would penetrate this insulating layer, finding deep-buried pockets of ancient hypervolatile ices like frozen nitrogen or carbon monoxide. These pockets, when warmed, would burst forth explosively, driving dust from the surface in violent, isolated jets. It was an ingenious idea, a way to reconcile a rocky appearance with cometary behavior. It envisioned the object not as a cohesive icy body, but as a kind of geological minefield, its interior primed with explosive traps set billions of years ago. This model explained the activity, but it struggled to account for the object's profound structural weakness. An ancient baked comet nucleus should be a hardened, sintered thing, yet 3I, Atlas, fell apart with astounding ease, crumbling into pieces as it coasted through the relatively benign environment beyond the orbit of Mars. The forces at play were minuscule, yet the object disintegrated as if it were made of loosely packed sand. The desiccated comet hypothesis, while clever, felt incomplete. It was an explanation that raised more questions than it answered. This forced us to turn the problem on its head. What if we abandoned the notion of a primordial body altogether? Primordial objects, the leftover building blocks from a solar system's birth, are mixtures of ice and rock. But what if 3I Atlas wasn't a building block? What if it was a fragment of a finished structure, a piece of something that had already formed, already differentiated, already lived a geologic life of its own? What if we were witnessing the arrival of a piece of an exoplanet? This was a staggering leap, a conceptual jump from the realm of cosmic debris to the realm of planetary forensics. The implications were immediate and profound. A planet, especially a small rocky one, is not a homogeneous ball of ice and dust. It undergoes a process called differentiation, where heavier elements like iron sink to the core, while lighter, silicate-rich rock forms a mantle and a crust. Such a world, forged in the fires of planetary accretion, would have long ago baked out its primordial surface-level water ice. It would be, for all intents and purposes, a dry, rocky body. If you were to take a piece of such a world and send it hurtling through interstellar space, it would look chemically exactly like 3I Atlas. Suddenly, the absence of water was no longer a puzzle. It was a clue. It was the defining characteristic of an object born not in the cold outer fringes of a stellar nebula, but in the warm terrestrial zone closer to its star. This new model, the planetary fragment hypothesis, unlocked a door to a far more violent and dynamic vision of the galaxy. But it still had to solve the two great riddles, its ghostly activity and its incredible fragility. For this, we had to imagine the cataclysm that could create such a messenger. Two primary scenarios presented themselves, each a vision of unimaginable cosmic violence. The first is a process of celestial cannibalism, tidal disruption. Imagine a small, rocky exoplanet, a world perhaps the size of our own moon or Mars, orbiting a star in a system with a massive gas giant, a hot Jupiter. If its orbit were unstable, it could be drawn inexorably closer to either its star or the giant planet. As it crosses a gravitational boundary known as the Roche limit, the tidal forces acting upon it become devastating. The gravitational pull on the near side of the planetlet would be so much stronger than the pull on its far side that the world would be stretched, distorted, and then violently torn apart. This process would be a kind of cosmic dissection. The planet would be unmade, its layers peeled away like an onion. Shards of its rocky mantle and crust, now freed from their gravitational anchor, would be flung outwards with tremendous velocity. Some would fall into the star, some would be captured by the gas giant, but a lucky few, accelerated by the complex gravitational dance, would be ejected from the system, entirely becoming interstellar vagabonds. A fragment born this way would not be a solid monolithic rock. It would be a rubble pile, a collection of boulders, gravel and dust, held together only by its own feeble gravity, and perhaps some weak, cohesive forces. It would be a celestial ruin, structurally compromised from the moment of its violent birth. For eons, it would drift through the absolute zero of interstellar space, its fractured interior frozen solid. Then upon entering our solar system, it begins to warm. The slight, uneven thermal expansion, the sunlit side warming while the shadowed side remains cryogenically cold, would introduce stresses throughout its already fragile structure. Microfractures would form and propagate. The entire body would begin to shed a fine powder of silicate dust from its disintegrating surface, a process of slow, inexorable crumbling that perfectly mimics a cometary coma without any need for ice. Its fragility would no longer be a mystery. It would be its defining inherited trait. The second scenario is even more dramatic. A direct planet-shattering collision. We see the evidence for such events in our own solar system. The prevailing theory for our moon's formation is that a Mars-sized body named Theia struck a young Earth, blasting a massive plume of mantle material into orbit which later coalesced. The asteroid Vesta bears the scar of a colossal impact that carved a crater nearly its own diameter. Now imagine such a collision in a young, unstable alien solar system, but on a scale that dwarfs even these events. Two protoplanets locked in a gravitational duel finally collide. The energy released is incomprehensible enough to melt and vaporize entire worlds. The impact sends a shockwave through the planetary bodies, shattering their rocky mantles and metallic cores. In the aftermath, a cloud of debris expands outwards. Much of it will eventually fall back to reform a new body, but a fraction of that shrapnel, accelerated past its star's escape velocity, is cast out into the galaxy. 3I, Atlas, could be one such piece, a fragment of a world that died in fire 4 billion years ago. Like the tidal disruption model, this explains its composition perfectly. It also accounts for its structure. A piece of planetary mantle violently ejected from a cataclysm would not be a solid, pristine rock. It would be a profoundly fractured object, riddled with cracks and faults from the initial impact. Its journey through our solar system would be its final undoing, as the gentle warmth of our sun proved to be the last straw for its shattered structure. The dust it shed was not the breath of a comet, but the very substance of its own slow-motion disintegration. It was the ghost of a murdered world. This new paradigm, born from the strange behavior of 3I, Atlas, doesn't just explain one object. It reframes everything we thought we knew about interstellar visitors. Suddenly, the profound weirdness of our very first guest, Oumuamua, begins to snap into focus. Oumuamua was also assumed to be a comet, yet it showed no coma. It was dark, reddish, and exhibited a strange non-gravitational acceleration, a slight push that defied explanation. At the time, with only the cometary model to guide us, scientists proposed everything from invisible outgassing of hydrogen ice to the infamous and unlikely alien solar sail. But what if Oumuamua was simply another, different kind of planetary fragment? One model, now gaining significant traction, suggests Oumuamua could have been a nitrogen iceberg, a solid chunk of frozen nitrogen sheared off the surface of a Pluto-like exoplanet. Such an object, when warmed by our sun, would outgas pure nitrogen, a gas that is transparent and incredibly difficult to detect, perfectly explaining its mysterious push without a visible coma. It too would be a piece of a larger differentiated world. The picture that emerges is therefore one of staggering diversity. The galaxy is not just flinging primordial snowballs at us. It is seeding the void with the entire gamut of planetary materials. The interstellar medium is not merely a repository of nebula leftovers. It is a graveyard, a cosmic debris field littered with the remnants of planetary formation, evolution, and destruction. We had been looking for messengers from the cradles of solar systems, and instead we have found ghosts from their battlefields. Comet Borisov, the one visitor that behaved exactly as we predicted now, seems less like the rule and more like the exception, a pristine survivor from a quiescent outer solar system. Oumuamua and 3I. Atlas, the anomalies, the weirdos, may represent a far more common class of object, born from the chaos and violence that seems to characterize the maturation of most planetary systems. They are telling us that the processes that shaped our own home, planetary collisions, tidal disruptions, the gravitational billiards of giant planets, are not unique. They are ubiquitous. We have moved beyond a simple taxonomy of comet versus asteroid. We are now dealing with a rich, complex tapestry of cosmic detritus. We might encounter interstellar iron cores, the stripped hearts of shattered protoplanets. We could see interstellar crustal fragments bearing the unique geology of a world we will never see. Each visitor becomes a message in a bottle, a geological sample from an alien world delivered directly to our doorstep. By studying their composition, their isotopes, their structure, we can begin to perform a kind of galactic archaeology. We can learn about the chemistry of other solar systems, the prevalence of water, the raw materials available for life elsewhere. 3I, Atlas, in its silent, crumbling journey, has fundamentally altered the mission. We are no longer just comet hunters. We have become interstellar prospectors, sifting through the galactic tide for clues about lost worlds. The implications stretch into every corner of astronomy, from our models of planet formation to our search for life. Because if the galaxy is freely exchanging the rocky material of terrestrial planets, it raises a question as profound as it is thrilling. Could it also be exchanging life itself? The journey of 3I, Atlas, may have ended in a cloud of dust, but the journey it has started for us, the journey of understanding our place within this vast, interconnected web of cosmic exchange, has only just begun. And so the phantom departs. A fleeting visitor from an unknown shore, 3I, Atlas, slips back into the silent, star-strewn ocean from which it came, its brief, incandescent passage through our lives now fading into memory. We are left behind on the pier, watching a ship disappear over the horizon, clutching the strange and wondrous cargo it unexpectedly left in our hands. It arrived as a whisper, a smudge of light in our most powerful telescopes, tagged with a designation that suggested we understood its nature. We called it a comet, imposing our familiar labels upon the unknown, comfortable in our assumptions. We charted its trajectory, predicted its behavior, and prepared to witness the routine spectacle of a celestial iceberg sublimating under the sun's glare. But this traveler refused to follow our script. It held its secrets close, wrapped in a shimmering coma of gas and dust that defied simple explanation until that final breathtaking glimpse of what lay within. What we saw there in the heart of that ghostly shroud was not the chaotic, tumbling nucleus of ice and rock we have come to know. It was something else entirely, something structured, something unexpected. And in that moment of profound revelation, our comfortable understanding of the cosmos was irrevocably fractured. The journey from that first faint detection to the final paradigm-shattering image is a testament to the relentless spirit of human curiosity. It is a story of how we chase shadows through the void, not for conquest, but for understanding. We began by asking, what is it? And we have ended by having to ask ourselves, what is? Times, everything times. Because the existence of an object like 3I, Atlas, does not merely add a new specimen to our cosmic museum, it fundamentally rearranges the entire exhibit. It forces us to reconsider the very processes that connect the stars, shape worlds, and could just possibly ignite the spark of life itself. This object was more than a geological artifact. It was a messenger, a time capsule delivered from an alien hearth across an unimaginable gulf of space and time. We now must confront the staggering possibility that the galaxy is threaded together by a previously invisible network, an interstellar transit system for the fundamental components of existence. For billions of years, we have contemplated the origin of life on Earth, wondering how a barren primordial rock transformed into this vibrant living world. We theorized that comets and asteroids from our own outer solar system acted as cosmic water-bearers and couriers of organic chemistry, delivering the raw materials for biology's great experiment. It was a local, almost provincial story of planetary formation. But 3I, Atlas whispers of a far grander, more expansive narrative. It suggests that the seeds of life's potential are not confined to the nascent dust cloud around a single star. They may instead be galactic property, exchanged between star systems, with a frequency we are only now beginning to appreciate. Imagine for a moment the journey, an object forged in the violent, chaotic youth of another solar system, ejected by the gravitational dance of giant planets. For millions, perhaps billions of years, it tumbles through the void, a silent, frozen arc. It endures the sterilizing wash of cosmic rays, the relentless vacuum, the deep, starless cold. A conventional comet nucleus, a fragile agglomeration of ice and dust, would be slowly eroded, its precious organic cargo degraded by this harsh environment. But the bizarre, resilient core of 3I Atlas hints at a new class of celestial vehicle, one seemingly better designed for the rigors of long-duration interstellar travel. Could its unique structure be a more effective shield? A natural vessel perfectly suited to preserving complex molecules. Molecules like amino acids, the building blocks of proteins or nucleobases, the letters of the genetic alphabet. Suddenly, the theory of panspermia, the idea that life itself can be transported between worlds, is revitalized, lifted from the realm of speculative fiction and placed firmly on the table of scientific inquiry. This is no longer a question of whether life's ingredients can survive a journey from the Kuiper Belt to Earth. It is a question of whether they can survive the journey from a world orbiting Vega or Polaris, or a star so anonymous it has yet to be named. Could it be that life is not a series of isolated, miraculous events, but a contagious phenomenon, spreading its potential from one stellar island to another? This single fleeting visitor forces us to look at our own world with new eyes. The water in our oceans, the carbon in our DNA, the very fabric of our being, we have always known it had a cosmic origin, but we assumed it was local produce. Now we must entertain the breathtaking idea that some of the key ingredients for life on Earth may have been interstellar imports delivered 4 billion years ago by objects just like the one that has now vanished back into the dark. We may be, in the most literal sense, the children of 1,000 alien suns. The implications ripple outwards, shaking the foundations of stellar dynamics. Every star system we have ever studied has been our own. Our models for how planets form, how systems arrange themselves, and what materials they are built from, are all based on a single solitary data pointus. We have been like a biologist, studying an unknown creature but only ever having access to a single cell. 3I. Atlas is the first sample of tissue from another part of the body. It is a direct physical fragment of another planetary nursery, and its composition is a chemical blueprint of its home. By studying the light reflected from its core and the gases boiled from its surface, we are engaging in a form of cosmic archaeology. We can begin to infer the chemistry of the protoplanetary disk from which it was born, the types of stars that illuminated its youth, and the violent dynamics that cast it out into the lonely darkness. It is a geological ambassador from a star system we will likely never see, and it tells us that our galaxy is far from a static collection of isolated stellar empires. It is a dynamic, interconnected ecosystem. Imagine a vast, invisible river flowing through the Milky Way, a current of matter composed of countless objects like Oumuamua and 3I, Atlas constantly streaming from one star's sphere of influence to another. Each star system is not an island, but a harbor on this galactic river, both contributing its own debris and receiving material from upstream. For eons, this process has been mixing the chemical inventory of the entire galaxy. Material forged in the heart of an ancient, long-dead star on one side of the Orion Arm could, after a long and meandering journey, become incorporated into a newborn planet on the other. This constant exchange means that the raw materials for planets, and perhaps for life, are far more homogeneous across the galaxy than we ever dared to imagine. The universe, it seems, is an obsessive recycler, ensuring that nothing truly goes to waste. The ashes of one solar system become the foundation of the next. This revelation forces us to redraw our maps of cosmic habitability. The famous Drake equation, our first real attempt to quantify the odds of finding intelligent life, is built on a series of variables: the rate of star formation, the fraction of stars with planets, the number of habitable worlds per star system. The discovery of a robust mechanism for interstellar transport fundamentally alters one of its most uncertain terms: the fraction of habitable planets on which life actually appears. If the chemical precursors to life are not rare, but are instead being actively and efficiently distributed throughout the entire galaxy, then the odds of biology taking root in any given suitable environment could increase exponentially. The galaxy might be far more fertile, far more primed for life, than even the most optimistic astronomers believed. 3I. Atlas does not prove that we are not alone, but it dramatically strengthens the statistical case that we shouldn't be. It transforms the void between stars from a barren desert into a potentially rich and fertile sea, teeming with the dormant seeds of possibility. And with that thought, a more tantalizing and unsettling question emerges from the shadows. If nature can produce such an effective vehicle for transporting the building blocks of life, what might intelligence construct? We scan the skies for radio signals and laser flashes, the techno-signatures of civilizations calling out across the dark. But perhaps we have been too limited in our thinking. Could an advanced culture seeking to propagate life or simply explore the galaxy engineer objects designed for this very purpose? Probes or arcs built to endure the ages, carrying a message, a genetic code, or even just the fundamental MAC, chemistry for life, to be seeded among fledgling star systems. Is it possible that among the natural debris flowing on this galactic river, there are also manufactured ships in bottles launched by hands unknown? When we looked into the heart of 3I, Atlas, and saw something that was not a comet, we were forced to expand our definition of natural. The next time we see such an anomaly, we may have to consider whether we are looking at a geological freak or a technological artifact. The line has become thrillingly, terrifyingly blurred. This is the legacy of our brief encounter. It has left us with more profound questions than we had before it arrived, which is the truest sign of a genuine scientific revolution. And now, as we stand on this new intellectual shore, we are not standing still. We are building a new generation of lighthouses, designed to scan the cosmic ocean for the next visitor, and the one after that, the Vera C. Rubin Observatory in Chile will soon begin its legacy survey of space and time, a monumental motion picture of the entire southern sky. Its all-seeing eye will catalogue billions of objects, detecting faint, transient visitors like 3I, Atlas, with unprecedented efficiency. What was once a serendipitous, once-in-a-decade discovery could become a weekly or even daily occurrence. We are about to witness the opening of the floodgates. When these new travelers are found, the James Webb Space Telescope, our magnificent infrared eye in the dark, will be ready. It will turn its golden mirror toward these fleeting apparitions, dissecting their faint light with breathtaking precision. Webb can act as a master chemist, identifying the specific molecular signatures of water, methane, carbon dioxide, and complex organic compounds locked within their cores. It will be able to tell us not just that a visitor is strange, but precisely how times it is strange, revealing the unique chemical dialect of its native star system. At the same time, the Nancy Grace Roman Space Telescope will cast a net 100 times wider than Hubble's, discovering thousands of new worlds and potentially catching even more of these interstellar wanderers in its vast panoramic gaze. We are moving from an era of passive observation to one of active systematic searching. We are no longer just waiting on the pier for ships to arrive. We are building a global harbor patrol. And even that is not the final frontier. We are now daring to dream of the chase. All over the world, engineers and scientists are designing missions with a singular, audacious goal: to physically intercept one of these objects. A high-speed probe, a celestial falcon that could be launched on short notice to rendezvous with a future interstellar visitor. To fly alongside it, to map its surface, to analyze its ejected gases up close, and perhaps, one day, to land on its surface and drill into its core, to bring a piece of another solar system back to Earth. Such a mission would represent a leap in our capabilities as profound as humanity's first steps on the moon. It would be the ultimate fulfillment of the journey that began with 3I Atlas, not just to see but to touch. To hold in our hands a pristine relic from a world beyond our own, a tangible link to another star. Our universe has once again revealed that it is far more complex, more interconnected, and more mysterious than we ever imagined. The story of 3I Atlas is not an ending. It is a preface to a new chapter in our exploration of the cosmos, a chapter we are only just beginning to write. It reminds us that the greatest discoveries are not those that provide all the answers, but those that shatter our assumptions and inspire a whole new generation of questions. We look up at the same night sky, but we see it differently now. It is no longer a silent, static backdrop of distant, disconnected lights. It is a place of unseen currents and hidden pathways, a dynamic space alive with the traffic of messengers from worlds unknown. And we, for the first time in our history, are finally learning how to read the mail. The search continues. The voyage has just begun.